Hello and welcome to another video. In this video we're going to be working on prime subtraction option. And in this one you're given a zero indexed array nums of length n, and you can perform the following op as many times as you want. Pick an index that you haven't picked before, pick a prime strictly less than nums I, and subtract it. And return true if you can make nums strictly increasing using this kind of strategy. And so let's take a look. So essentially to tell you what to do here, so you can basically subtract 3 here, and this will turn into a 1. And you can subtract 7, get a 2. Subtract 3, get a 3. Actually, I don't think you can just stop here technically, and then you have 1, 2, 6, and this is increasing. Okay, so in this one, you can subtract 5, get a 1. Subtract, you can't subtract 7. So I guess we would subtract like something like 5. Or actually, this is already sorted. Actually, so never mind. Yeah, this is already sorted. But even if it was already sorted, so for an array that's already sorted, I think there's always a way to make it strictly increasing. Could be wrong about that. Yeah, maybe I am wrong about that actually. But yeah, so this is already actually sorted, so it doesn't matter. In this one, so we would want to subtract 4 to make it a 1. And then we'd want to, actually, sorry, we can't subtract 4 because 4 is not prime. So the most we can subtract is 3 to make it a 2. That means here we can't subtract 7, so we'd have to subtract 5, make it a 3. And then here there's nothing we can subtract because 1 and 0 aren't prime. And then, yeah, you can't, so basically, I guess it doesn't matter, you can't subtract anything. This is the smallest these two can be, and then this one is already a 3, so you can't make it bigger. So like, yeah, it's not possible. So I guess the simpler version of this problem is we can forget about these prime numbers, and we can just say like, okay, given an array, let's see here, given an array of numbers, suppose we can just subtract any number we want, or 0, and we want to make the result strictly increasing. So if we just had like 9, 2, 5, 1, 7, something, you know, like if we could subtract any number we want, what would we do? As long as the number is smaller than our current number. Well, we can just kind of do the greedy thing, right? Where we can just make the first number a 1, second number a 2, and so on. So we can subtract 8 here, make it a 1. Keep this number the same. Subtract 2 here, make it a 3. And then here, we can't do anything, so this kind of broke, right? So we weren't able to do this. But if this didn't exist, like let's say this was our array, then we could subtract 3, make it a 4, and then subtract nothing. All right, so that's kind of like the greedy approach with subtracting. And with primes, it's kind of similar. Like we kind of just want to subtract the biggest thing possible to make it as small as we can. But you need to know like what prime can I subtract. So there's kind of 2 ways to do it, and I think one of the ways is pretty rare to use. So I kind of want to describe that quickly. And I think it's called like the sieve of Aristophanes or something like that. It's actually kind of a simple algorithm, but it's pretty rare to see. So I'm just going to quickly describe how it works and then show like what we can do and so on. So let's say we have the numbers 0 to 9 and we want to know like what's prime. Like this is very good for given a range of numbers, determine the primes, and it has to be a continuous range. And that's kind of the case here. Like let's say our array is like 1 to 1,000,000 or something. Like the smallest number is 1 and the biggest number is 1,000,000. We'd want to figure out like what numbers in here are prime, so then we can figure out what to subtract. Otherwise, we'd have to go through every single number and try to like subtract numbers and see if they're primes, right? And that honestly will pass. So you could say like, if I have 10, let me just subtract maybe 9, like is 9 prime, is 8 prime, is 7 prime, just go through all of them. And that would actually pass, I think, too, but it's kind of better to pre-compute this ahead of time, and then we can kind of just check if these things are prime, because we're going to be reusing a bunch of numbers, or we can. So the way this works is pretty simple. Basically, we can mark 0 and 1 as non-prime, and then we're just going to loop from 2 on to the end of the array. And we're going to check, so initially we're going to mark everything as prime, so we'll just give everything true as in it's prime. And we're basically going to check for a number if it's prime or not. So we're going to loop going one at a time. And if the number is prime, that means all multiples of that number are no longer prime, right? Like if 2 is prime, that means 4 can't be prime, 6 can't be prime, and so on. So that's kind of the algorithm. You just go forward, and anytime you hit a number that's not prime, or that is prime, then you jump through every multiple of it and you mark it not prime. So for 2, we would just say like, okay, 2 is prime, fine. Let's just go to multiples of 2. So we'll just keep adding 2. So we'll mark this not prime, this not prime, this not prime. Then we'll go to 3, and 3 is prime, so we'll mark 6 not prime, and it's already marked not prime, and 9 not prime. Then we'll go to 4. 4 is not prime, so we could skip it. 5 is prime, so then we'll go to whatever. There's nothing here, and then we just keep basically doing that. So that's kind of the basic algorithm: is you go to a number, you check if it's prime or not, and if it is prime, then you just jump that amount, and then you mark everything. And then this becomes complexity-wise if you think about it. So our initial pointer goes through it once, and then for every single one, you're going to jump through multiples of that. So it's kind of like n log n. It's going to be actually a little bit faster. Like normally n log n is like log base 2, but because we're jumping, sometimes we're jumping at multiples of 2, sometimes 3, sometimes 4, sometimes 5, and so on. It'll actually be like a little bit faster than log base 2 of n because the log number will be bigger. But roughly this. So then we're going to have this like array of, the smallest, or every single number in our thing, and if it's prime or not. So let's just go back to this example. Maybe I can do this and do this. Okay, so essentially we're going to have this thing, and we're also going to have the number 10, and 10 will not be prime. So we'll put it here. And now we kind of know what we need to subtract. So there's kind of 2 ways of doing it. There's like the, I want to say, more intuitive way, and then there's like the better way. So the more intuitive way is we can take all of our primes and make a new array. So we can just say like, okay, all our primes here is 2, 3, 5, 7, that's it. And we can do this in like O of 1, right? Or not an O of 1, we can just go through here in O of n. So like 2 is a prime, 3 is a prime, and we can just store these in the array, right? And then 5 is a prime, and 7. And so ideally for this one, we want to make the value a 1. So we want to basically figure out, we want to make the value as small as possible. So we want to figure out like what's the biggest prime we can subtract that's 3 or less. And because these primes are sorted, that's just basically a binary search, right? We're looking for the biggest number 3 or less. We can binary search this guy, and then get that. And then we'll say like, okay, we actually found 3. So this is a 1. So now for this number, we can't subtract 8 because it would make it a 1. So the lower bound here is 7, and the upper bound, the biggest number we can subtract is 7, and then the smallest number we can subtract is 0. So ideally we want to subtract the biggest thing here. And so you can kind of do this binary search again, like what's the biggest number we can subtract, and you'll get a 7, and then you'll also make sure that like it also satisfies the lower bound. I think it's like 2 binary searches or something like that. And you can keep doing this. You can keep doing this. You can keep getting like a lower bound based on the previous number and the upper bound based on the current number. And then just see like, how did this work? There's kind of like a better way of doing this. So the better way of doing this is instead of binary searching all the time, and also I guess I briefly wanted to mention why this works, like looking at the constraints. So you, like I said, you want to look at the constraints first, and you want to figure out like, time complexity and all that. So the biggest number is 1,000. So 1,000 log 1,000 is fine to do this like sieve of Aristophanes, like that, or something. I never pronounce it correctly. But yeah, this is called like the sieve of Aristophanes. You can look it up. So yeah, so this is like 1,000 log 1,000, which is fine. And then the binary search, there's going to be, like how many primes are there in 1,000 numbers, not too many. That's also fine. Yeah. And then we can also kind of figure out like what numbers we want based on the numbers in the array, right? They can only be 1,000. So instead of doing this binary search, we can just try to manually change these numbers to something else. And we can just keep increasing it. So let me kind of show what I mean here. And this one's a little bit tricky to find out. So if you didn't think of this one, you can just do the binary search. I think the coding part of that's a little bit harder, but the intuition's a little bit easier. I think the easiest thing is probably just manually brute force actually primes. That's probably the easiest. So like if I know like I have a 9, I'll just check like is 8 a prime, 7 a prime, 6 prime. That's probably the easiest implementation. The sieve of Aristophanes is like the second easiest with the binary search, intuitive wise, and this is the hardest, but the coding part of it is not so bad. So yeah, so if I have this array, I'm basically going to say like, let me just make the first number as small as possible. And so I can't make it a 0 because I can't subtract 4. But I can just keep track of a number here, and I'll just say like I want to make this like cur or something. I want to make it a 1. And so to make it a 1, I figure out like what's the complement I need, like what do I need to subtract to make it a 1. This is kind of like the two sum basically. So I need to subtract 3, and then I can just check like is 3 prime? Yes it is. So if 3 is prime, I'm going to make this a 1, and the current number I made is a 1. So now the next number is going to be a 2. And then same thing, we're going to see, can we make this a 2? So to subtract 2, we'll make it, we'll need to subtract 7. 7 is a prime, and we're going to have this like array or hash map, whatever, all our primes. So we can subtract 7, get a 2. Now the next number we can use is 3. And then here, can we subtract, so to get a 3, we need to subtract 3, which is fine. 3 is a prime, so 3. And the next number, 4. And so here, to get a 4, we need to subtract 6. 6 is not prime. So then we're going to keep increasing this current to try to get the next one. So we can't get a 4, maybe we can get a 5. To get a 5, we need to subtract 5, it's fine. And you notice that like we could have just done these two, and then this would have been fine, but you can just manually try to make these as small as possible as well, like it'll give you the same thing. So we were able to get this thing done. So let's walk through the next couple examples. So example 2, there's 2 more numbers. So let's add those as well. And I'm not going to show like how we got those, but we already know that like how this works, and then 11's prime, 12 is not. Okay, so our numbers in this case are 6, 8, 11, 12. Okay, so we're going to check. Remember, we're going to want to make this as small as possible, so we'll just start with a 1. So to subtract 1, and we can reuse primes as well, so that's also fine. So to get 1, we need to subtract 5. 5 is a prime, fine. Now the next number we're going to try to get is a 2. To get 2, we need to subtract 6. 6 is not prime, so we're going to increment. And once cur can never be bigger than like the number we have. So once cur is we can't make this number any bigger than 8, right? We can try to make it smaller, but as soon as cur becomes like 9 and this is 8, then we basically have a no solution. So if we want to make it a 3, we have to subtract 5. 5 is 5. 5 is prime, so we can do that. And so the next number we can use is 4. So for 4, this needs to be 7, and that is prime, so we can make it 4. Now we have 5 available. So 5, we need to subtract 7, and we can do that, so 5. And so this is done. Now also notice this was sorted already, and you can check for that, but if it was sorted already, I'm pretty sure you can always do this as well. Yeah, because you can just like not change the number. So you can just like basically one solution would be like subtract 0 from all of these or something. So I think, yeah, definitely if they are already sorted, you will basically just like one of the solutions subtract 0, but there might be some other one. Okay, so finally let's look at the last one. It's the same thing, 5, 8, 3. Okay, so we're going to try to make this a 1. We can't because 4 is not prime. So let's try to make it a 2. To do that, we need to subtract 3. We can do that. Okay, so this has to be a 3. So this is basically just greedy, make this as small as possible, and then current can only go up to 1,000 because the num's length is only 1,000, or num's I, sorry, is only 1,000, and we can't make numbers bigger, right? If current is like 10 and our number is 8, then we have no solution. So we're going to only increment this up to 1,000 times, and then the array is only 1,000 length, which is like fine. Okay, and then, yeah, so this needs to be a 3. We can do that. We can subtract 5. 5 is prime. And then here we have no solution because cur needs to be 4. So it needs to be 4. It's 3. We can't increase the number, so we're basically failed. So hopefully that makes sense. Let's take a look at the code. So first we're going to get the maximum of the array. Then we're going to make this array of primes. So here, and then we're going to basically set everything equal to true. And we're going to set primes 1 equal to false and keep prime 0 equal to true because you can subtract 0. Because subtracting 0 just means not changing the number. You can't subtract 1, but you can subtract 0 and you can subtract a prime. Then we do the sieve of Aristophanes, so basically loop from 2 to the end of the numbers. I think you can technically loop from 2 to the square root of the numbers, is fine too. It's kind of the same thing as the prime factorization, you only need to loop to the square root, but it's fine anyway. And then you just basically check, is this number a prime? If it's a prime, we're going to go up that number until we get to the end, right? So if it's 2, we're going to go to 4, 6, 8, 10, whatever. If it's 5, we're going to go to 10, 15, 20, and so on, and mark them all false. Then we have our current, we start at 1, and we go through the numbers and we check if our current number is less than the number, but the complement we need is not prime. Let's just keep increasing the current number until we get something that works. And then once we ideally have something that works, we check if the current number is bigger than our number, then we failed. Or if that difference that we found is not a prime, we failed as well. And if we succeeded, then we'll just increment current to the next available number. And then if we were able to go through all these numbers and satisfy this like complement being prime, then we can return true. And so we can submit this. Yeah, so let me look up the title of this guy. And I have used it, I want to say 4 or 5 times, and it is kind of good. So I guess it's kind of like 2 pointers, but this is the one that I was meaning. Eratosthenes. Yeah, Eratosthenes, okay. So yeah, this is basically just, if I have a continuous range of numbers and I want to figure out what's primes, this is the way to go. If you want to figure out, for a number, is it a prime, then you can just do a prime factorization. But in this case, we're going to have the same numbers we're going to be reusing, so better to cache them. Obviously, you can just make a DP function that does the prime factorization, or not a DP function, just a function that does prime factorization and cache results there too, which would be fine as well, but this is like a little bit more efficient. Either one will pass because the constraints are kind of easy for this one. So brute force, prime factorization, this, whatever you want. Or also that doing this sieve and then doing the binary search. Basically, literally, anything will pass for this problem. As long as you do a reasonably efficient prime factorization, it's fine. Okay. So let's go through the time complexity and all that. Okay. So this is max nums. Like we're basically going from 0 to max nums. You can make it less if you want. You can go from like min nums to max nums or whatever. Actually, no, you can't. I think you have to go from 0 to max nums. Making this primes is max nums as well. Yeah. So basically, this whole thing depends on like what's the biggest number in primes, and then making the sieve is a log of max nums times max nums. Yeah. And then going through the numbers is O of n. And then this curve can get incremented up until max nums. So that's just plus another max nums, but this thing is bigger. So it's something like this. Max n, I guess. Something like this. So log of max n times max n plus n. Space. So we're storing this primes array that's up to the biggest number in primes, and I think that's all. So this is just max nums. Yeah, and because this is so small, then this is fine. So definitely constraints are the way to go here. If this was like 10 to the 9th or something, you wouldn't be able to do that. You would want to actually get the prime factorization of every number then, because the prime factorization of a big number is okay, but doing the whole sieve for 10 to the 9th would time out. So it is important to know like what kind of stuff you want to use based on these different constraints. And yeah, it's going to be all for this. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.